Testing, 1, 2. Okay, this is our second lecture in a subject called the calculus of variations, and today I'd like to do a couple of applications in how this came into prominence in physics. So I'd like to just maybe do a brief little chart of sort of where we've gone in the course, and so you can see sort of the evolution of some of the ideas we had. So back in the early days, we had the Greeks, and we had owed to them geometry and the axiomatic approach that comes along with Euclid's elements. And this is essentially the same approach that we use now. And where I want to go with this is that geometry, and then of course we developed algebra, and functions. And we combined these ideas with the Greeks' ideas of geometry into coordinate geometry, so these together led into coordinate and analytic geometry. Now, as soon as we add calculus into this, these together will form a nice blend of differential approaches and algebraic geometry. This in turn led to the concepts of of surface and curvature. So we have curvature and other related ideas, which we then saw once we added into variational methods, which are sort of the integral equivalent to the critical point condition f prime equals 0 at a max or a min or extreme point. So we have variational methods. And then what I led up to last time was we added in some conservation laws of physics. And then you had some minimization principles, like principles of least action. This led up into modern physics. With the ideas of Einstein, which essentially looked at the relationship between curvature of space-time, where we live, is essentially equivalent to gravity. And the idea of conservation, or invariance in this case, of the speed of light, led into special relativity. And finally, what we talked about, if you add into these ideas, if you throw into the mix the ideas of quantum mechanics, which come from the very earliest ideas of atoms, from Democritus, throw those into the mix in the sense that you have quantum ideas, This essentially gives you all the ideas of the modern explanation of physics. So this gives you the unification of modern physics, chemistry, engineering, etc. And so this essentially gives us our pictures of the universe. So in the very real sense, the Greek conception of the universe, and I don't mean that they thought the world was round or something, but you had the very primitive ideas of atoms and rigorous mathematics. And even the idea of experimentation and verifying ideas with evolved over time into this modern conception of thought, which explains everything from black holes to quarks to all this kinds of stuff. So, sort of what we're seeing here through this course is the gradual development through history of the earliest thoughts of atoms, geometry, axiomatic approach, adding into it a little bit of the symbolic and algebraic component of mathematics, evolving into a much more powerful geometric approach, combining functions and algebra and geometry, then getting into surfaces and higher dimensions, seeing the role of the actual world in physics and these very nice laws, conservation of energy, conservation of mass, etc., leading into modern physics, and then reinserting the ideas of curvature and surfaces, geometry of surfaces, led Einstein to postulate his great explanations of why the speed of light's constant in all reference frames and why space is curved and why that leads to gravitation. And then going back and adding one more idea of the atoms into the new form of quantum ideas, quantum mechanics, leads you into the modern idea of thought. So just as a plug, this Saturday, Stephen Hawking will be giving a talk at Texas A&M. I don't know if it'll be recorded, but I hope it is and put on the web, because that would be well worth listening to. He'll be speaking Saturday, which is what day? The 8th, I guess, at 4 o'clock at Texas A&M. And he'll be addressing Gödel and the end of physics, which is a really interesting because it would tie in with the ideas of this course, I think, quite a bit. So I don't know if he means Kurt Gödel in terms of the incompleteness theorem. Kurt Gödel, by the way, was a mathematician, and one of the earliest things he did was work on Einstein's theories of general relativity, and he postulated some questions and specialized solutions of these problems. So he and Einstein were both at the Institute for Advanced Study in Princeton at the same time. Okay, going back to less sort of grandiose ideas, I found a few references that kind of tie together nicely some of these ideas of mathematics and physics. So I want to just move through here. The first one is a link between optics, and by optics I mean, Snell's law and the idea of geometrical optics. Now, this is actually a picture of Richard Feynman here. It's kind of interesting. He's an interesting character, and this is Fermat. Fermat postulated the principle of least time, meaning that light will travel from A to B in the path it takes the least time. So, for example, when you have density variations in the air, light rays don't go from the sky straight to your eyeball in a straight path, because cooler, or a hot surface will actually bend the path because the density of air is less, and so the speed of it will change in such a way that you'll actually see a mirage. So you'll see light from the sky get bent down near to the ground, and your eye, when you're looking down and you see the sky, you see blue on the surface, and that looks like water, so this is essentially a mechanism for what we know as mirages. Now you can actually derive the principle of Snell's law, or the idea that you reflect off at equal angles of incidence and reflection, because if you look at all paths that connect A to B through straight line segments varying along the surface, if you look at the length of the path, assuming light travels a constant rate, the distance or the path will be shortest whenever this makes equal angles. And you can actually show that as a problem in calculus, because the total travel time is a quadratic. Here it is. If you graph that, it will take on a minimum at the point when the angles are equal. Now that's assuming, of course, that the speed of light is constant in both mediums. So if you're reflecting from a surface, that's true. But suppose you have two surfaces like air and glass, where the speed of light is different, then the light ray will be bent, because even though the straight line path here is shortest in terms of geometry, it is not shortest in terms of time. So in order to go from a minimum travel time, you would actually have a bent path, and these angles are related precisely by a minimization, which leads to Snell's law of reflection. And I think, yeah, this is actually Snell's law here. The sine of the angle of incidence is equal to the index of refraction times the sine of the angle that's transmitted here. You can also show that, for example, when you have reflection off a surface, if you have a parabolic mirror, light rays that come in on straight lines are all focused in on a single point. Another way of saying that is if you had a candle or a laser here, the light would be focused out in a straight line. If you have this. So when you have starlight coming in from an area here, it all gets concentrated photographically at a small little image here, or radio waves, for example. And one of the very last things that's kind of interesting, you can approximate a mirror by a spherical mirror. It's hard to grind a perfectly parabolic mirror. But one of the things you can observe is that if you spin a fluid at a constant angular rotation, the surface of the fluid will be parabolic. So if you take a beaker of fluid and you give it a rate of rotation in here, then the fluid will actually be bent in a parabola. Now, if you could actually have a shiny fluid, you could actually make a parabolic mirror this way. And in fact, at the very last part of the article, it says that they took 28 liters of mercury, which is a rather large amount of, that's 14 2-liter Cokes of mercury. That's a lot of mercury. If you put that in a container and spin it 1 revolution per 8.5 seconds, and they give a website here, you can use that as a parabolic mirror because it's a very smooth surface. But there are obvious safety considerations, so you wouldn't want to. You can only have it vertical, right? Because if you have it at an angle, the gravitational effects will distort the surface. So it can only point straight up. But it's an interesting idea of a parabolic mirror, or a parabolic surface, I should say. Let me move that away there. Whoops. Okay, so it's a parabolic surface. Another application that I wanted to talk to, we mentioned this before, is just a nice little introduction to Feynman's path integrals. And this is a little slideshow. And they relate the path integral Now some of this may be a little bit technical, so let me move to this psi function here, capital Psi, depends on x and t. It is a solution of the so-called Schrödinger equation, and it moves forward in time by the action of this integral, where you integrate this known function here against the wave function, and it tells you how it evolves in time. And they actually wrote down. Now these are the various paths that Feynman would allow you to integrate over. And if you sum the probabilities over, they will essentially cancel because of the phase. And this is actually what G is. It looks like this 1 over 2 pi I, difference in times, exponential. And you can combine this with the principle of least action, which we've already seen, and the ideas of Lagrange's equation, and then this propagation operator, and then end up with a path integral. And if you sum all these over, essentially what you get is the resultant path. Now, I'm not going to go through the whole thing there. I'll leave that up to you. But this is a nice little, if you're interested in, if you've heard of something called the Feynman path integral, you can look at that and see how it ties into topics that we talked about. Now, one of the ideas that modern physics really is based on are what I would call some of the great ideas. They're not problems, but let me call this classical physics. So you have the idea of conservation of. And what you could conserve in classical physics was, for example, mass. Obviously, classical physics did not allow you to create or destroy atoms at the atomic level. That's nuclear physics or quantum physics that tells you that. But Newtonian physics, I should probably call that Newtonian physics. You have conservation of mass, conservation of momentum, conservation of energy. And it turns out if you just impose these ideas, the laws of motion would then be derived just from postulating these great ideas. So from a simple idea, will automatically, without any kind of ambiguity, would give you well-defined equations of motion. Now, as an example of how that works, I'll show you sort of how this works. Suppose we just start off with a blob here, some volume at time 0, and it has some mass. So this is the mass of the volume at time 0. Now, you know how you can integrate something to get the total mass, because what is the density? The density is mass per unit volume, right? That's the definition. So if you look at mass as the density times the volume, a little bit of mass, delta m, is going to be the density, rho, times the volume, or expressing this as an integral, m is the integral of rho times dv. Okay, well that's very nice. What about, let me copy this here. What about if we change this surface? It evolves according to some law. Where did it go? Trying to move this up. It pastes where it came from, I guess. Okay, move this back up to here. Okay, so what happens if this volume at time 0 evolves into some really kind of deformed volume at a later time. Well, it's still true that, I mean, if you can't create or destroy atoms, that this is going to be equal to the density at this new volume at a later time, for all time. Positive. So, in other words, there's as much mass in this blob as there is in this blob, and remember, the density can change. Now, how do you handle this? Well, remember from calculus, if I have a point x, y, z here, it'll be mapped to a point u, v, w, where u is a function of x, y, and z, v is a function of x, y, and z, right? And w is a function of x, y, and z. And how do we write dv as du, dv, dw? This is capital V. I claim that just from your change of variables, or the Jacobian UVW xyz times dx, dy, dz. Now remember what this is. This is just the determinant of the Jacobian. So that's the determinant of du dx, du dy, du dz, dv dx, etc. It's a 3 by 3 matrix. But you see, this matrix contains all the information that you need to say how the system evolves. Because using this identity that du, dv, dw is equal to the Jacobian times dx, dy, dz, I can substitute it in here. And what I get is that the mass, which is a function of x, y, and z in my original coordinates, is just through a change of variables, rho of u, x, y, and z, v, w, times the Jacobian times, which is a function of t, times du, well, it's mapped back to dx, dy, dz, so dx, dy, dz. So what does that say? It says that the density, rho of x, y, and z, essentially becomes this quantity here. So this tells you how the density evolves. Okay, this says that rho at your new position equals 1 over this Jacobian times rho at your initial position. So what this says is, if you know how this mapping goes, how this surface deforms, it exactly tells you how the density deforms. Now in particular, if the mass doesn't change, what is its derivative in time? If m equals a constant, what is the derivative with respect to t? Well, it's 0, right? So that means the total derivative d of v0 rho times dx, dy, dz, which is, this is 0, which is also a derivative of V0 rho of U, V, and W times J dx dy dz. Since this is over a constant surface, we can pull this inside. And finally, we use just the chain rule. The total derivative is what? It's the partial derivative with respect to time plus d by dx, dx d by dt, right? Plus dy dt, d by dy, plus d by dz, dz dt. Just by the chain rule. And what is dx dt? This is the velocity. So this is d by dt plus u, the velocity u, times the gradient of this. So the gradient is d by dx, d by dy, and d by dz. And this is just the dot product, which means you take the first component, etc. Okay, so now what we have is that this total derivative, d by dt of rho j, is partial with respect to rho j plus u dotted in with the gradient of rho times j equals 0. So this actually tells you how the mass evolves. So the transformation, which is really the geometry, how the geometry is changing in time, gives you one of the equations of motion. Now, also, go back here. Suppose there were sources. Now, what does a source mean? A source means that suppose you have like a straw in here and you're putting in fluid into a big tub, or so there's actually a source of mass in here. And then you have to integrate the source over the volume. So if I were to actually change this to the change of the mass equals some integral of some source over the volume, plus maybe something that's happening over the boundary, then you can see this becomes what? This becomes f times dv over the boundary. And what is this is really the integral of the divergence of t over, if this is t dot n, this is really the divergence of t over the volume, right? By one of the theorems in calculus, third semester calculus. So what you have in here is you'll change this, you'll add terms to the right. So that becomes f plus divergence of t. Okay, so this gives you how source terms that are acting on the surface, affect one of the equations of motion. Now you can do the same thing with energy and momentum. So do the same thing. Oops, can't write a D. Do the same thing with momentum. Which is, after all, the integral of rho times u dv. And energy, which is like rho 1/2 u squared. And look at the derivative here. And you'll end up with a system of equations. You'll get 3 equations for here. You'll get one for energy and one for mass. So you end up with a system of equations which essentially governs any solid or liquid. Now gas is a little bit different, because gas you can't treat as a continuum, because these derivatives now become sums over the molecules and you need statistical mechanics and stuff. So possibly a dense gas, but not a gas like we normally think. But a solid or liquid, these essentially, what I've done, and very quickly, is showing you how physicists and engineers derive the very foundations of continuum mechanics, which is the equations of motion for a solid, and fluid dynamics, which is obviously for liquids. Right. If you have shock waves and things like that, what that leads to do is these equations can be, well, if they're dependent on time, these equations are normally what are called hyperbolic or possibly diffusive parabolic. It depends on if they allow shock waves or not. But these equations, if your u is going fast enough, you can actually get a shock wave. In fact, that's actually a good point. Let me just show you one of the simplest equations of motion that can give you this is called Berger's equation. And that's in one dimension, just d by dt plus u ux equals, say, 0. Now, this is a very simple application. This is du dt plus du by dx. Now, this is nonlinear. There's a u times ux, but it's exactly this form, right? It's d by dt of something plus u dot something. So if this something were proportional to u, you would get this equation, Berger's equation. But look at what this is. I can write this. If I look along a curve, dx dt equals u, then I claim this is d by dt, total derivative of u, is the partial derivative of u times u gradient u, which in this case is du dt plus u ux. So what this says is it's 0. So this equation says that along this line, dx dt is constant, given by that value. This says that du dt is 0. And if du dt equals 0, u equals constant. So along this line, u equals constant. So if u is positive, dx dt is positive, and you have u going this way. If u is negative, what happens? Dx dt is negative. But what happens to these lines? Eventually, those two lines are going to do what? They're going to meet. But what happens if they meet? Because here u is positive, here u is negative. What happens there when they meet? No, they won't cancel out. I mean, there's a problem here. You have a function which is taking on positive and negative values at the same point, and this is in time. This is in x. So here there's a discontinuity. So this point here, u is both positive and negative, which means I have a discontinuity. Now, discontinuity in physics is a shock. So what this really is saying is that you have a wave that's developing, like you get a little blip like this, and then a little bit further in time the wave steepens up, and then eventually it gets straight, and then if it were to go a little further it would become like this. But this function is not single valued. There are 1, 2, 3 heights. There are 3 different values of u for the same x position. So the development, this is a shock, and this is a multi-valued solution. The multi-valued solution is not really allowed by this particular solution. You can get a nice solution up to this point, and up to this point the solution, classical solution, ceases to exist. Because why? Because what's the gradient here? What's du dx? Du dx becomes infinity. And if you have a solution of the equation where one of these terms becomes infinite, it's a singularity, and the equation and the assumptions that you use to derive this equation are no longer valid. Okay. That was a long little segue, but what I wanted to indicate is that just from these simple laws of motion, namely something is conserved, namely mass and energy and momentum, you can derive equations of motion that govern most of the laws of classical Newtonian physics, continuum mechanics, solid dynamics, and fluid dynamics. And in fact, they can lead to equations with very interesting behavior. For example, shock waves, and where the classical solution fails. So the point is a very simple idea, namely conservation of mass, can lead to complex physics. And now this is very elegant. I mean, you can just talk about the ideas of conservation of momentum, conservation of angular momentum, linear momentum, energy, etc., but it leads to the actual laws that we do observe. We actually do observe these laws. Now, if you have a very simple model which predicts complex physics very accurately, what does that tell you about the model? Well, remember Occam's razor, always go with the simplest explanation, keep it simple, stupid? That's Occam's law says that if you have a very simple idea, like conservation laws leading to very accurate portrayals of very complex nonlinear physics, then you really are onto something. You really have the main idea here. And this was a triumph of mathematics and classical mechanics. This is what is called mechanics in the physics sense. Well, the constancy of the speed of light doesn't really come into Newtonian physics because it says that because your mass stays constant, it doesn't change, right? Mass is conserved. If your mass doesn't change, it just takes more and more energy to accelerate. There's no upper bound on your velocity. But Einstein said that no, nothing can move faster than the speed of light, and as you move things up to the speed of light, the mass gets heavier and it takes more energy to move it. There's more inertia, and that puts an upper bound on the speed of light. There's no upper bound on velocities in classical Newtonian physics. That was something that Einstein postulated, that the speed of light was constant in any reference frame that you could do physics in. Now he arrived at that, interestingly enough, not from any mathematical principles, but just from more or less thought experiments. He would think of, well, suppose that were not true, then he could think of a situation which would lead to something contradictory. And so he said, well, in order to eliminate all these kind of philosophical contradictions, he had to assume the constancy of the speed of light, and then when he assumed the constancy of the speed of light, out pops special relativity. and E equals mc squared as a consequence. Now I do have a nice little link to those things in physics which are conserved. What are they? Well, I don't get into baryon number, that's particle physics. Charge, color, this is actually not color like, conservation of purple. This is the color of quarks. So these are all theoretical nuclear physics kind of stuff. But conservation of energy, that's something we understand from regular physics. Conservation of mass, conservation of momentum. Strangeness number, lepton number, isospin, don't worry about those. Those are all, again, quantum mechanics and theoretical. The ones we're interested in are angular momentum, energy, mass, and linear momentum. Those 5 principles actually will lead to pretty much all of classical physics and mechanics. Now I should mention that if you do a count of the equations of motion, you get one equation for mass conservation. So this is the number of equations, and this is conservation of. You get 3 equations for linear momentum. You get 1 equation for energy, and then there's also some angular momentum, but let's just suppose we stop here. We'll end up with 5 equations. Now if you count the number of things that are not known, like rho, the velocity, if you do a count, there are more unknowns than there are equations. So what happens in mathematics if the number of unknowns, I can't spell unknowns, if the number of unknowns is bigger than the number of equations? Can you hope to get a solution to this set of equations? No. If the number of unknowns is less than the number of equations, it's overdetermined. If the number of unknowns is bigger, it's underdetermined. We want to make it equal. Well, how do you make the number of knowns equal to the number of equations? You add in additional equations. Not additional unknowns, that's the wrong way. You want to add in additional equations. Now, we saw a little bit of it here. If you go into this one place where I have this surface term, where is that? Yeah, right here. Here's a quantity called T. That is the relationship between forces on the surface and how the motion behaves. Now, you cannot deduce this from first principles. There is nothing that tells you how the material will behave because of applied forces. Now, if I suppose, let's see, where is that? Yeah. So, for example, T, this term, a relationship between applied force and resultant motion, is this deducible from first principles? No, because it depends on your motion, right? If you apply a force to a beaker of liquid, that's certainly going to be different than applying a force to a piece of steel or a rubber band or silly putty, right? The relationship between applied force and resultant motion is what's known as a constitutive law, because it tells you what constitutes motion. Constitutive relation. Well, see, kinematics is just, it's telling how the particle would respond to motion, yeah. And for example, how does the particle depend on temperature? How does the particle relate to gravity? Or how does the particle relate to chemical reactions or something? All of that are additional things that are not deducible from first principles. They depend on the material. So this is where all the physics is in this constitutive relation. And in fact, for that matter, it's where all the engineering is. So the physics and engineering come in at this point. Up to here, it's been strictly a mathematical exercises. This holds for any material, any density, any volume deformation, basically behaves like this. This is just a property of the integrals and Gauss's law and the divergence theorem and things like that. Here is where you start getting in the actual particular piece of material that you have in mind. And this, adding in more equations, is what they call in mathematics closure. So for example, the Navier-Stokes equations you get by applying this principle to a fluid. And it just has to do with a different constitutive law. So those simple conservation laws lead to very, very complex physics, very interesting mathematics. I found actually a reference. This is a free book, online physics book. This is kind of nice because it's one of these sort of, it's in a PDF format, which is nice, but you can download it to like your PDA or your laptop and actually read it online. So if you click on the download link, this is the conservation of energy, conservation of momentum, etc. There's a download somewhere. Where's the download here? Yeah, here it is. If you click on download the book, it's a PDF file. It'll take just a little bit. It's about 1.8 megabytes. But it actually is nice. It's very nicely colored. While I'm waiting for it to download, I'll just finish up this discussion here. So what we've seen here is we've had a very nice application of this idea of conservation and applying, in this case, not something as a minimum, but something as a constant, which is even a stronger constraint. We've arrived at some very nice equations of modern physics. Here it is. It's downloaded here. So this is a nice book. It's an online book. It has some really great illustrations. Now, I'm not sure. This is it's supposed to be, I guess, a hurricane, and this is part of a sunspot, so I'm not sure what exactly it is, although it's a really nice illustration of something. So conservation laws, let me just shrink this down to, let's see, I think that I need to zoom in a little bit. This gives you a series of introductory physics books on Newtonian physics, conservation laws, vibration waves, electricity and magnetism, optics, and modern physics. So this is actually a free set of books online. You can go to that Light and Matter series and download all of these and print them out. But they have a nice little, I guess that's Newton's apple there. This is probably should be some copyright deals here. This is acknowledgments, imputases, lots and lots of, there we go. So conservation of energy, momentum, angular momentum, they have exercises, information, data, etc. So you can actually go through here. And I like it because the PDF format, you can download these. It's really nicely illustrated. Some cool looking pictures here. So we're not going to discuss anything more about this. What I want to do is just give you kind of a very quick overview how very simple ideas of mathematics can lead through some very simple transformations into some very complicated equations that govern physics that are very, very accurate. As long as your material doesn't break apart, as long as you're not trying to accelerate it to the speed of light, where you have quantum mechanics or relativity interplay, this really does govern the laws of observable macro-scale physics. And in one sense, this is the triumph of mathematics and physics, and led some people to believe that basically physics was a completely closed system and completely deterministic. So I would point out as my end that up till Einstein, I'd say up till the late 1800s, people were predicting the end of physics. And by that I mean the fact that there would be nothing more, and maybe this is related to the talk of Hawking's as I think about it, but this was a premature prediction because they pretty much thought it was a determinate system. That means given the equations which they thought they knew, and given the initial conditions, all it took was just solve the equations and you could predict anything. You would have completely determined physics or laws of motion. Then Einstein came in and said, whoa, you can't do that. First of all, there's this thing called the uncertainty principle. You can never know the initial conditions precisely. Second, the equations are much more complex, and they have to be invariant under these certain relativistic transformations, and now flat space is no longer flat, it's curved. So right now, in the early 1900s, it moved to the point where physics is over to someone asking Eddington, who was a mathematician at Cambridge, saying that he had heard that there were 3 people in the world that could understand general relativity in 1920. In other words, 3 years after Einstein formulated it. And so you have special relativity in 1907, and in 1917 you had general relativity. These completely changed physics. I mean, they rocked it on its ear. Not because anything like the mathematics had changed, but the whole ground rules of physics had changed. So into the late 1800s, people said, oh, if we just could solve the mathematical equations, give the initial conditions, we could predict anything arbitrarily far in the future. Well, we know that's not true now because of quantum mechanics, Heisenberg uncertainty principle, etc. And then when you add these things, in 1920, probably only 3 people in the world understood general relativity. I mean, understood it in the sense that Einstein understood it. Einstein was one, this mathematician called Eddington, and in fact, one reporter said that he'd heard only 3 people understood general relativity. Eddington said, I know I understand it, Einstein understands, but for the life of me, I don't know who the 3rd person is. So that was maybe an apocryphal story, but it led to the complexity of, it was such a complex mathematical theory that no one could handle it. But now, in 2003, this general relativity is essentially taught to second-year graduate students in physics and mathematics. So general relativity is essentially studied by graduate students. Granted, not your graduate students of, English, but graduate students in the appropriate disciplines, math and physics. And this is what gives people hope that even though the theories are getting more and more complex, people like Stephen Hawking and other people are trying to simplify the complexity to say, look, really, there are only some really fundamental ideas, and if you have the mathematics, those simple ideas sort of evolve into this very complex thing, but it's still, the underlying principles are simple and not complex. And that's what we hold out as the hope. And this is where, going back to the first page, it's very nice to have this historical viewpoint that when you're a Greek, this idea of Euclid's geometry was like general relativity. It was this horribly complex, very beautiful, very elegant, explained a lot of things, but who could do it? And then 100 years later, it was taught in the Greek academies, and then 2,000 years later, it was still being taught essentially unchanged. And then people discovered more ideas, more complex things, folded them in until gradually you came back to some very simple ideas. It got more complex again, and then it got simple. I think we're right now in this very complex world. In other words, what we've done, unfortunately, we started off with simple ideas in the Greek, got complex, got simple again, got complex again. So if this were Greeks, this would basically be Newton. Then this would be basically Einstein. Then this is probably where we are now. We're waiting for the next sort of great simplification. And what people are really hoping for at the bottom of this is, and I'll end it here, is the UFT. Anybody know what UFT is? Unified Field Theory. Now this is supposed to be the theory of everything. In other words, one theory of physics that will explain everything from gravitation down to what holds protons and neutrons and quarks together. And we don't have that yet. There are actually 3 forces out of the 4 that are known. Gravity is the longest range. Then there's electromagnetic. That's like charge of, cannot spell. Electromagnetic, gravity, electromagnetic. This is radio waves, electromagnetism, charges of electrons. Then there's the weak nuclear force. This is what holds protons and neutrons together inside the atom. And then there's these strong nuclear or strong interactions. These are what keep the quarks glued together to form the fundamental particles. Everything in the universe is thought to compose of quarks, and things like protons are composed of quarks. Neutrons are composed of quarks of different colors and spins and shades and numbers, etc., colors. Everything in the universe is explained by quarks, and actually people know how to combine these theories, these and these and these. So we're 3 out of 4, so maybe we're down here. But this is the big thing. No one knows how to combine gravity and these guys, because this is on the order of 10 to the minus 30th, and this is on the order of 10 to the plus 20 in terms of scale. So you're trying to get a unified theory of physics that will explain everything over 50 orders of magnitude, including quantum mechanics and general relativity. So who knows? And this is what Hawking probably will talk about. I'm not going to speak for him, but some of the greatest ideas of mathematics have resulted because people postulated problems whose solution led to complexity. Other people came along and simplified things and said, hey, it's really not that complicated. What really is going on is that we have these great laws of conservation, of energy and mass, etc. And now we have Einstein that says, look, we have this constancy of the speed of light, curvature of space due to gravity, etc. And now we have this complexity and now we're simplifying. So this rise and fall of mathematics is in part due to what this course is about, namely problems. Great problems lead to simplifications of understanding. If you can explain the solution to a very difficult problem very simply, you've probably discovered something very fundamental. Okay, so I'm going to end at that. I do remind you that there is homework assigned for today. If you can't get it in, I would encourage you to just take your time and do it correctly. I've posted at least one hint for problem 11.2, and I will post solutions later on over the spring break. But if you can get it in by Monday of spring break, do the best you can, and we'll take it up to Monday, postmarked, emailed Monday.